Good morning, mathematicians. Hope you're all doing well. Hope you all proved lots of things yesterday and in the previous week. I I did the Calgary Tower again yesterday, and I'm less. I guess I did it better because I'm less completely drained of energy this time. Edit Smith, how are you so on the ball? You're so on the ball every morning. It's impressive. Okay, what to yap about today? Well, there's something I was thinking about. A nice little theorem. See if I remember how to prove it. Let's see if I can crack through it on live. So there isn't a nice purple in dark mode. Well, we'll stick with this. So one theorem that I like thinking about module categories and functors between them and different kinds of functors. And in particular, actually, this is something you can define for any category. So suppose you have some category. That's my attempt at a fancy C. And suppose that you have the identity functor on that category. Then you can look at the collection of natural transformations. Right, basically the Hom set in the functor category of the identity functor. So, in other words, this is the collection of natural transformations from the identity functor to itself. And in general, this will be a monoid under composition. Can you ask me something about the derived category? Sure, please do. Please do. I use it all the time. I use it daily in my research, but well, it's less mysterious to me than it used to be, but it's still yeah, I don't know. I don't consider myself an absolute pro with the derived category, but I will definitely ask your question and I will do my best to answer. Well, I'm waiting for that question to pop up. I'm just going to keep yapping about this for a moment. So this is called, and this is sometimes called the center of a category. The center of the category is defined to be this. And so, well, the claim, maybe this is the reason why it's called the center of the category, but it turns out that the center of the category of R modules actually has not only is it a monoid, but it has a ring structure, and as a ring, it is isomorphic to the center of R, to the center of the ring you started with. And this is actually an idea that allows you to prove the theorem. So for commutative rings, this is not true in general, but I like thinking about the general case. For commutative rings, R is isomorphic as a ring to S if and only if the the module categories are equivalent. Oh, the Abel Prize was just awarded to Masaki and Kashiwara. Thanks for letting me know. To be honest, I don't know who Masaki is, but I definitely know Kashiwara. Let's bring that up. Abel Prize 2025. Okay. Cool. Kashiwara is actually related to what I was talking about, I think, yesterday or the day before, D modules. He's a big D modules guy. I've read somewhere that the purpose of derived category is the usual derived functor lack of something, but it's not explained explicitly. Could you elaborate on that? I have some familiarity with ext. Yeah, so I mean, there's a lot one could say about the derived category. I don't know if it's about the usual derived functor lacking something. I mean, maybe there is a legitimate perspective about the usual derived functor lacking something. That's not the perspective I have. There's sort of two main things I could say. I could tell you about why we might care about citing the derived category. So one is just the general idea that we're interested in cohomology theory. Right? So well, for simplicity, we could just stick to, say, like a category of R modules, right? And we're interested. Yeah, his advisor was Sato. Yeah, Kashiwara Saito. In fact, there's a paper that is very important to. Sorry to get sidetracked here for a second, but there's something called the Kashiwara Saito singularity. You know, they sort of did it independently. You know, it's just some sort of geometric thing to show that, you know, there's this special kind of singularity. But here's actually a paper from my supervisor, collaborator, and a friend, who, so in this paper, well, they do stuff relevant to my work, so it's stuff about, like, you know, the varieties I was talking about, and like Langland's type stuff. But the thing is, they prove that one of these varieties has an instance of the Kashiwara Saito singularity, and that actually has consequences for the representation theory that we do, which is yeah, pretty cool. And if I understand correctly, this kind of singularity manifests in the real group's case as well. But yeah, sorry, I'm gonna jump back to cohomology for or derived categories. So yeah, obviously, yeah. So cohomology is important in all sorts of stuff, right? We talked about yesterday that there's cohomology theories you can attach to topological spaces. Of course, cohomology can be useful for modules. You know, you said you're familiar with ext, right? And in some sense, ext measures the failure of a module to be projective or injective, right? The Tor functor measures the failure of it to be flat. So, so there's all these sorts of uses for cohomology. But, you know, oftentimes what happens, like, so if you think about the way that you determine X of M and N, of two modules M and N, let's say, right? So I'll probably say things backwards. There's all of these left-right conventions, and I always forget which way to write things. But I think normally what we do is we put the projective resolution over here, right? So you can do a projective resolution or an injective resolution, but it doesn't matter. So the point is, you first take a projective resolution of M, then of N, and then you apply the. I must be. I think I'm doing it backwards, but whatever. Up to. I need to switch the way that I'm doing it. Then you apply the Hom functor with M in the first component, right? And now you get this other complex, and then your X is just defined to be the cohomology of this complex, right? And so the thing is, it didn't really matter. Right? It didn't really matter what complex we took. We just wanted, all it needed to be was a projective resolution. That was all. It didn't. So there's some theorem that says, if you had chosen a different projective resolution to start with, then you still get the same X group up to isomorphism, right? So this sort of makes us start to think, oh, okay, well, there's this whole theory of chain complexes. And so, there might be multiple chain complexes that we could take, but we don't really care up to, like there's a sort of equivalence we might put on the chain complexes up to the cohomology that it gives us, in this instance, right? So one thing we can do is we can sort of formalize this study a bit, right? I mean, so if we have some category of R modules, we can form the category. I mean, the chain complexes themselves form a category, right? So there's some sort of structure there to study, and it's certainly relevant to understanding the cohomology theories that we want and whatnot. So so we realize, chain complexes, right? Those are objects unto themselves, and we can define maps between them, which are just, maps at each level, commuting with the differentials of the complex. But now, so we can just study the category of chain complexes as is, and just the ordinary, we can look at isomorphisms of complexes in the ordinary sense. But we know that isomorphisms of complexes are too strong for us, right? The thing that we really want is something we basically want to say that two chain complexes A and B are equivalent, or maybe form a new category where they're isomorphic, if and only if they're homology or cohomology groups, whichever way you're writing it. If their cohomology groups are isomorphic at every place, right? And that's the basic idea of a derived category. So we have to do some work to make this precise and rigorous, but the basic idea is that the derived category, the objects are still just honest to God chain complexes, except now we introduce more maps. So we say, for instance, that it's possible to find, say, a map of chain complexes, which is itself not an isomorphism of chain complexes, but for which the induced map on the cohomologies is an isomorphism. And so that's what we call a quasi-isomorphism of chain complexes. And basically what the derived category does is there's various different formulations. There's various different ways to make this rigorous, but the derived category basically takes quasi-isomorphisms and just like formally makes them have an inverse. So I think, yeah, I actually have a video on derived categories. I think the thumbnail is me and a cat with laser eyes. So you can learn a little bit more about one of the approaches to this there, which is arguably not the approach that most people prefer nowadays. But it's sort of maybe the most down-to-earth approach to constructing the derived category. So, in my opinion, that's motivation number one for studying the derived category. Motivation, but there's other motivations as well. Actually, I don't know if I know a good way to justify this from a very intuitive level, but there's this term you might know that gets tossed around a lot called the six-functor formalism. Thanks for the explanation, but I still don't get it, since from my naive perspective, the localization category is just formally invert those maps. Yeah, that's true. I mean, that's an accurate understanding. But how do we actually get something from it? Yeah. I mean, well, what's a good I'm trying to think of a good way to sell this to you, to pitch the derived category. I was about to talk about a six-functor formalism, but which is important, but it's also, I don't know. I could see it if like I explain this and he'd be like, yeah, okay, maybe that's cool, but like, so what? Well, okay, so let me try and sell this in some other ways. So for instance, so right before you asked that question on the stream, I was talking something about how for commutative rings, R and S are isomorphic if and only if their module categories are equivalent, right? Okay, so you could, if you wanted, like when it comes to commutative rings, basically turn that into like a completely categorical study, if for whatever reason that tickled your fancy. But now, if we drop the commutative, we only have one of these implications. It's possible to find examples of non-isomorphic rings whose module categories are still equivalent, and that is something called Morita equivalence. And so then it's maybe an interesting question to ask, well, what ring theoretic properties are preserved under Morita equivalence? Some are, some aren't, right? Basically things that can be formalized categorically. And there's a whole bunch of interesting stuff in the Morita theory, and it is useful for the study of rings. I think it even comes up. There's something related to the Brouwer group, which I hear about all the time and read about all the time, but I've never really learned and understood properly. But I know the Brouwer group is important in number theory and stuff, and so the Brouwer group also has connections to like Morita theory of algebras. So there's a lot of important stuff there. And actually, I have a lot of questions about Morita equivalences, and I think there's cool things still unexplored. Just asking about what Morita equivalences look like. I mean, I know there's Morita's theorems. Anyways, okay, I'm not gonna get too distracted. But so some people say So I remember seeing this comment on Stack Exchange where someone was like, "Yeah, well, Morita equivalence isn't that interesting because you can't even change the dimension of modules. Like if you apply a Morita auto equivalence to some module category." Actually, I don't even know if that's true. Is that true? Anyways, they said something along these lines, and I was like, meanwhile, I mean, part of my research is actually basically boils down to, if you have two rings that are isomorphic, what does that isomorphism do when you pull back modules along it? And figuring out what it does is actually like kind of important and subtle in some cases, and not so obviously easy. Not for me, anyways. But okay, so some people say, Morita equivalents, like, are there weaker equivalences we could take? And yes, indeed, there's something called derived equivalences. And one of the advantages of derived equivalences, so that would be that if instead you don't ask that the module categories themselves are equivalent, but you could say, well, maybe the derived categories of these modules are equivalent, and you can go on to ask the same sorts of questions. Is like, well, what do we know? What can we say about two rings whose derived categories of modules are equivalent? Are there ring theoretic properties there? I don't know as much about this. I know that this is an area of study, and people are like more interested in that than the module, or sorry, than Morita equivalence. Partly because there's a sort of weaker version, but something that very much still happens on the level of derived categories called Koszul duality, which one of my mathematical peers at in my research group is working on, has a paper on Koszul duality. And Koszul duality has so there's some notion of being like a Koszul algebra and having its Koszul dual, and there's deep relationships between the modules over this algebra. And in fact, so my own research is about the p-adic Kazdan-Lustig hypothesis, and I went to a summer school recently last summer, about the notion of Koszul duality, and the classic version, which is applied to what's called the BGG category O. So I think I talked about this yesterday. Do I still have the note somewhere here? Yeah, the Kazdan-Lustig hypothesis, which basically is an effort to study like G modules for some Lie algebra, like representations for this Lie algebra, and actually part of proving the sort of classical Kazdan-Lustig for this Lie algebra involves using this notion of Koszul duality. So it actually leads to a pretty powerful theorem in representation theory. Yeah, Morita equivalence is cool. Actually came up with this question yourself. Awesome. It's always great to come up with your own questions. That's, I think, very important. But not dig to the point derived thing until now. Yeah. Okay. So hopefully that gives you a better idea, somewhat, of why. I mean, I would. So I'm just spitballing here about my own personal perspectives on the derived category and like how derived categories impact my life, but is probably worth looking up. Like I'm sure someone has written like a history of derived categories, and is probably a good idea. I might even do it myself to look up like what was the actual historical motivations behind defining the derived category. My guess is that it just goes back to this idea of complexes and realizing, chain complexes are and something interesting that we want to study, and if you only care about what the cohomology of your complex is, and not so much the actual objects in it. Quasi-isomorphism is a natural equivalence relation to put on it, and so you might be tempted to study this category. But yeah, I don't know the true historical motivations. And then it's also just, aside from the initial historical motivations, it's just ended up being really, really useful. So I will just quickly say there is this six functor formalism. So for example, like, well, even if we just go down to the level of rings, right? There's sort of, if you have a morphism of rings, we get, speaking of Morita theory, we get a bunch of interesting functors between these module categories induced by this morphism, right? So we have like the restriction of scalars, an extension of scalars, and a coextension of scalars, right? And I think I always forget which way the adjunctions go, but again, just maybe they go in the opposite direction, whatever. But we get this nice sort of triple adjunction of maps. It turns out, though, so you might wonder, you say, okay, there's an F lower star, an F upper star, and an F upper shriek. Maybe there should also be an F lower shriek. And it turns out that generally speaking, well, actually, I don't know, maybe it does exist just on the level of module categories, but in generally, no, there isn't an F lower shriek. Well, not in the module categories, but actually it turns out that there's a derived functor that has these nice adjunction properties. And this is the same for if we had some morphism of like schemes or something. Well, I mean, what are sheaves on a scheme but generalizations of modules, really, right? And again, we get, some adjunctions of morphisms between the sheaf categories. I don't have videos on these ring functors, but I've been thinking of making some, just because, yeah, they're cool. So I will maybe I will make some videos about them. So I struggle with like, what video should I make and how much effort should I put into it? I'm like, I gotta write my thesis. I gotta like maybe teach myself math, finance, or cryptography to go get a non-academic job later. Or maybe I should ignore everything and just focus on getting the best academic job possible. So we'll see what happens. But I have a hard time shutting up about like cool ring category functors, so we'll see what happens. Anyways, the same thing happens on this level. Actually, sometimes F lower shriek can exist on the level of sheaves. I can't remember what the condition is, but if X and Y are like certain kinds of spaces and F is a particular kind of map, it's in a Char's book, then F shriek can sometimes exist on the level of sheaves, but it doesn't always exist on the level of sheaves. However, all of these functors do naturally also induce functors on the level of derived categories. And when you go to the level of derived categories, now you'll have an F shriek that always exists. So it's kind of like there's a thing. So even if you didn't believe in derived categories, at least to start with, you know that we have these useful functors to pass between, like, say, sheaf categories or module categories, and between sheaf functor categories and module categories, and then you might realize, oh, sometime this F shriek exists, right? And sometimes you can apply F shriek to a sheaf and get out a sheaf, but sometimes there's this thing that you apply F lower shriek to F, and you end up getting out this complex of sheaves, right? And so you're just sort of like naturally forced into a world of complexes of sheaves instead. Jose, my main homeboy, my main man, coming through in the chat. Another reason for derived categories is maybe it allows you to get dualities you couldn't obtain before. Yes, like Poincare and Verger duality. Yeah. So, yeah, what he's talking about there is there's these Poincare duality theorems, which honestly I don't even remember the statement of. I'm a bad geometer. The Poincare duality. And it's a nice theorem for, say, like smooth, sheaves on smooth manifolds, smooth complex manifolds, or like smooth algebraic varieties or whatever. But as I mentioned in my research, we're interested in studying the meaning of these singular points in varieties and the implications that has for representation theory. And so it would be nice if we had Poincare duality theorems for manifolds that were no longer smooth. And it turns out, again, we do if instead you allow yourselves to work with yourself to work with complexes of sheaves instead. And so, for example, that's actually where sort of perverse sheaves come in. Is they satisfy this sort of duality, this Verger duality, which is like an analog of Poincare duality. But perverse sheaves are complexes of sheaves. They live inside a derived category of sheaves. And there's more stuff there. I mean, they technically form a heart of a T structure, and all this stuff. But yeah, when I see two functors that are an adjoint pair, what is your gut feeling about it? What do you expect to happen, and what do you do with them? I don't know this. I felt so disqualified as an algebra guy. Hi, Jens. Yeah, so I mean, there's a few different ways I think you can think of adjoint functors. So one way is, of course, like if you have two categories, and you have a pair of functors realizing an equivalence between them. Well, then it's pretty easy to pass information back and forth, right? Maybe they're both module categories. You can take this module over one ring, turn it into a module over another ring, and pass information back and forth, right? Maybe one ring's presentation is a little bit easier to understand than the others, and so you might, but maybe for some reason you need two different presentations of your ring, and you'd like to be able to translate between modules over each of those rings, right? So pretty easy to do if you have an equivalence, but maybe you want to understand more, like maybe you don't have an equivalence, but you still have a way of passing information back and forth, and the adjunction just allows you to preserve more information. So, like for one example, if H is a subgroup of G, let's just say finite group, then we have an adjoint pair between the categories of representations where we have our induction functor taking us from representations of H to G and our restriction functor, right? And if you're trying to like build representations and like search for irreducible representations, you might want to know, hey, if I have, so again, I'm going to mess up the left-right adjunctions here, but potato Picasso, hey. So let's say you want to know, well, does say I've got this irreducible representation pi. I want to know if I started with this representation sigma of H and I induce it, Then one way I could sort of measure if pi is in here is I could look at the Hom from pi into this induced representation. I mean, basically the dimension of this Hom set is going to tell me how many times pi shows up, at least if we're in the semi-simple category. Life gets more complicated in other cases, but it tells me how many times pi shows up in here. In general, it tells you how many times pi shows up as a sub-representation. Well, one of the great things is that if we have this tool, because maybe this induction is mysterious to us, right? But restriction's a lot easier to compute. So if you already knew, if you had a good understanding of pi and a good understanding of sigma, then by the adjunction property, you know that this is going to be isomorphic to the Hom, or now this Hom is happening in the category of representations of H. You can compute the restriction of pi and check to see how many times sigma shows up in that. And so that might actually be an easier thing for you to compute. And so here we've used an adjunction to actually better understand the way that representations, the way that representations sort of fit together in the category of G with the representations in the category H. And this is also important too. Say, for example, we have an adjunction between like representations of a Lie. So there's the category of representations of a Lie group, and then the category of representations of its Lie algebra. And we have functors going both ways, but they're not equivalences. But it's pretty close, right? Like we can essentially reduce most of what we want to understand about representations of Lie groups to the study of Lie algebras, which is fantastic because Lie algebras are like it's all sort of linear algebra, and so you can like computerize it and stuff to help you. It's not an equivalence, but it's something closer than just nothing, right? Like you can have two categories that are very, very different, and then just weird functors between them. Okay, the most related a category could be, well, the most is an isomorphism, but that's too strong, so we talk about an equivalence. And an adjunction is some sort of thing in between. It's some sort of compromise. It's like, okay, well, it's not an equivalence, but we can preserve a significant amount of information nonetheless. And maybe one last thing I'll say. So, on this topic, let me redraw the functors here. So, again, I forget which way the left and right goes, but there's equivalent definition, like there's equivalent ways to describe an adjunction, and one is to talk about it in terms of a unit and a co-unit. Well, first, let's just recall that if F and G form an equivalence of categories, that means that there's a natural isomorphism from F composed with G to the identity on D, and I'm going to write the other one in the opposite direction. You'll see why in a second. And there should be a natural isomorphism between the functors composed in the other direction, right? So this is what it means to be an equivalence of categories. But now we might ask for the slightly weaker result and say, okay, what if, maybe both of these aren't equivalences anymore, but maybe we just have the existence of some natural transformation between these pairs of functors. And that's an equivalent way to define an adjoint pair. And so one of these would be called, again, I always have to relook up the which one's which, but one of these is called the unit and the other one's called the co-unit. I think this one's the unit, but don't quote me on it at all. I have no idea. But this is an equivalent way, and so you can see how it's like a very gentle sort of weakening at each step, right? So first, an isomorphism of categories says that these functors both have to be equal. Okay, that's too strong, so we scrap it. We say, okay, now I'll look at an equivalence. That is so cool that OneNote knows that I want to erase it just by scribbling. That's amazing. We're living in the future, guys. Right, so then we weaken that a little bit more to get an equivalence of categories. And then finally, we might push the limits a little bit more yet and say, okay, what if these weren't isomorphisms? And delete. There we go. And we just say there were some morphisms here, and that's exactly equivalent to being an adjoint pair. So that makes it a little more precise what I was saying about how, adjunction is this compromise where it's like, okay, we know that these categories aren't equivalent, but clearly there's some sort of deep relationship. There is some sort of significant connection. How do we codify that? This is one way to do it. Thanks. Well, I'm glad you appreciated it. Glad it was helpful. Glad it was helpful. Yeah. Yeah. Yeah, let's jump over to the news for a second. Let's jump over to the news and take a look. Kashiwara received the honor. I love, by the way, speaking of the Abel Prize, there's so many great interviews. The Abel Prize interviews. I love watching them. You should go check it out. Abel Prize interview. Yeah. Look, there's a whole playlist. I mean, there's ones. You got Atia, you've got Ser, you've got Deline. Great interviews. I should go back and rewatch a bunch of them. It's awesome. Can this be done with any algebraic object? I'm not sure what be done with any algebraic object. Yeah, I'm not sure what the question. Do you mean like adjunctions, or I'm not sure, unfortunately. If you can add some clarification, maybe I can better answer your question. Yeah, let's look at this. Kashiwara. Oh, this just says Kashiwara. Wait, I thought there was two people. Oh wait, that's his first name. Oh my god, I feel so stupid. Yeah. Okay. Awesome. Right. Yeah. Reducing isomorphism to less restrictive equivalence. Yeah. Well, let me say something. This isn't well, it's kind of algebraic. Well, it depends on your perspective, but let me draw a total a complete analogy here. So say we have two categories, then we can have let me write it this way, or okay. We have F, we have G, and then those categories are equivalences. If we have isomorphisms here and here, let me draw you an analogous picture. Consider two topological spaces. And consider a pair of maps going in either direction. And if those maps, of course, if we have it could be that we have an equality between the compositions of these maps, in which case we would have a homeomorphism of topological spaces. But there's also a notion of morphisms between continuous maps, and those are called homotopies. And so instead, if we have a homotopy equivalence in either directions, then we say that these two spaces are homotopy equivalent. And well, this is more than an analogy. I mean, this is sort of like the key to why modern homotopy theory these days is basically category theory. But okay, maybe you don't consider that algebraic, but certainly there's all sorts of weakenings that you can do, right? I mean, so we expressed one weakening here in terms of weakening like equivalences of categories. We also talked about earlier about how we can the definition of a derived category involves weakening the notion of equivalences between objects. And one of the things, so there's like an approach to homotopy theory or infinity categories as well in general that talks about what is it called? It's called crap. What's the name? Something categories. Something I can't think of it. But basically you write down a class of maps that you consider fibrations, a class of map that you consider cofibrations, and then a class of map that you think of as weak equivalences. Okay, they don't have to be, if you happen to know what fibrations and cofibrations are in terms of topology, they don't have to literally be that, right? This is something you can, I think maybe this is called a quasi-category. But you write down these collections of maps. It's just some name, they satisfy some technical condition, and then the weak equivalences are sort of like the things that you want to force to be equivalences. Well, in fact, you can take, so any category. I forget the details now, but if you look at my video on derived categories, I talk about localization in categories in general. Like if you take any category, you can under some certain assumptions, you can take a class of maps that you decide that you want to be equivalences, and then you can basically take all of your Hom sets, and like as long as those maps satisfy some, satisfy that, you can put some equivalence relation on those maps, and it's like compatible with composition and stuff. Then you can form a new category, which is called the localization. I'll just write it like this. There's other notations, but where you just basically collapse all of those maps under an equivalence class. So you can do this in like all sorts of worlds, algebraic or analytic. Wish there was some type of sieve of objects until it will make them completely different objects. Yeah, reducing isomorphism, less restrictive to equivalence. Yeah, well, there is something called a sieve in a topos, in topos theory. That's also something I kind of want to make videos about, because it's something I want to like, maybe that's a direction I should take my sheaf series videos in. I don't know. So many directions it could go. So much time. So little time. Do I have a set of conjectures that am motivated to prove what motivates you and your team's work? Well, I can't speak for everyone on my team. If Jose's still in chat, maybe he can drop his response. But do I have a set of conjectures that I'm motivated to prove? I mean, kind of. I mean, there's like the Langlands conjectures. But I don't know if I mean, people are making progress on that. That's not really, I actually take that as given for my work. I mean, well, my thesis started trying to sort out what the Kazdan, the Piatek-Kazdan-Lustig hypothesis. And the point of my thesis originally was to figure out what's known and maybe prove more cases of it, which is like Yeah, I think basically the okay, it's complicated, I think, to say what is and isn't known and like what exact perspective. So the point of my thesis paper is going to, well, at least just say some definitive stuff about GLN for a p-adic field. Um, there's more to say. There is more that's known, but just kind of like dotting some I's and crossing some T's um, on that topic. So that's a little bit what I'm personally motivated by. But more generally, I would say that the my group is very motivated by something called Arthur packets. So James Arthur, who's my mathematical grandfather, um, he sort of came up with these ideas of Arthur packets, and they're it's some sort of way of like defining a collection of representations for a real or p-adic group. Doesn't have to be GLN, and they're sort of like special representations that there's some relation. It's not like a direct correspondence, but there's some relation between unitary representations and special factors of like automorphic representations. And there's a bunch of important conjectures around Arthur packets. And then David Vogan, he proposed a way to he defined these things that we now called, well, not just him actually, it was Adams, Barbash, and Vogan. So there's these things we now call ABV packets. And there's this conjecture that ABV packets, in certain cases, correspond to Arthur packets. And the point of this is that these are defined entirely geometrically. Okay, we don't know this in general, but my friend and colleague Ph.D. Ray proved this in her Ph.D. thesis for the case of GLN. Who, by the way, I interviewed her on my channel. She's one of my interview guests. So, I think she's currently working on pushing more cases of this result with some other people, but I wouldn't say like that's the main thing that's driving us, but rather it's just the general study of ABV packets. So that's maybe like a fundamental theme in my research group. Is studying these ABV packets. Of course, these are closely related to the Kazakhstan-Lustig hypothesis. Like they're both very much related to the geometry of these like moduli spaces of Langland's parameters. So I would say for our research group, like. I mean, yes, there's more concrete theorems I could talk about that it's like, oh, we're trying to prove this theorem, but it's also in a sense exploratory, right? We're sort of at the edge of things that are known, and so we're trying to like, so there's theorems that people in our group are attempting to prove, but we're also just trying to like find new ways to compute stuff, and we're just trying to like check things and just like see what's there and come up with guesses about like what this corresponds to and what that corresponds to, and so on and so forth. So from my experience, how would someone get all the prerequisites to the point that can do a paper? I mean, that depends on so many things. Like, it depends on, depends on the field, what paper you want to write. So, I mean, I guess in general, how do you get all the prerequisites? Like, go to grad school. I mean, there's a lot you can learn on your own, and you should be learning on your own, like outside of what you have to learn for school. But yeah, that's the point of having a research supervisor, whether that's undergrad research or in grad school. It's like you have a pro that guides you through stuff and sort of helps build a royal road for you to walk along. And royal road, not in the sense that it's easy, but there's research is fairly impenetrable, and they can help guide you into like a path. So yeah, just keep learning, and I don't know, keep in mind what fields interest you, and just like the terms that come up again and again, it's like, okay, well, I better have a pretty strong fundamental understanding of these words that I keep seeing in like abstracts that I look at and stuff. How did I get into literature for that hypothesis? God, I don't even know. Well, yeah, from lots of different places. So I would look at there's a paper called like the Piatek-Kazdan-Lustig hypothesis by Zelowinski. That's probably the number one place to look, and then attached to that. So definitely Zelowinski. And definitely there's also papers of Bernstein Zelowinski on called like induced representations of p-adic groups, where they develop the theory of multi-segments. So those are like foundational papers, but they can be sort of hard to read. You need some like a little bit of background in representation theory. Actually, there's also a paper though that's called like Representations of GLN by Bernstein Zelowinski. That's maybe not the most modern way of writing things, but you can get some basic definitions from there. So that's one place to start. I would take definitely the main place you should start is the paper called like Piatek-Kazdan-Lustig hypothesis by Zelowinski. But then, yeah, I don't know. It's how did I do the learning for it? I mean, it's very sort of by osmosis, like learning from people in my group and my supervisor, and reading little tidbits of that textbook and this textbook until I had like enough pieces of information. I'm also not a pro in the classical Kazdan-Lustig hypothesis, but that came first, so it's worth looking into like the original Kazdan-Lustig hypothesis for like the BGG category O, and just getting a high level understanding of like the main ideas there. Sorry, let me scroll up here. I know commutative algebra is not your field, but how far do I have to go after mastered standard texts like Matsumura? Mass stack exchange scares me always, since everyone seems casually. Yeah, well, hey, look, about people knowing more than you, that's always going to be true. So you just gotta accept it, rip that band-aid off, deal with it. There's always like, probably to some of you it seems like I know so much, and I'm like, oh, I know all this like crazy math, but like, I go to conferences and I'm just like humbled by like there's people that just like they're younger, they're like much younger than me and know like infinitely more than me already. There's always someone better than you at everything. Same thing. I go to the gym every day and I'm liking the way I'm starting to look. But there's also people that are just like infinitely more jacked and will always be. And that's fine. You just gotta deal with that. You gotta get over it somehow. Yeah, how much further do you need to go? I mean, I don't know. I don't know. Because research is also different than mastering a textbook, right? I mean, the best thing you can do is just go to archive, search commutative algebra, see what people are working on, and just sort of start there. So, yeah. I don't know. Again, that's also why like you kind of need someone to guide you, like a supervisor, because they're going to be the one who can answer that sort of question for you. Tried learning it a while back, got to the end chapter 2, I think it was on Picard-Vesiot theory, and I just quit. Wasn't that interesting? Yeah, I mean, sometimes if something's not that interesting to you, you're not going to be able to learn it. I think it's good to try and force yourself to learn some things you don't love that much. It's like, I don't know. I mean, I like broccoli, but I don't know. If you don't like broccoli, you still make yourself eat broccoli. It's good for you. I'm glad that you learn everything, or you learn something new every time I have my office hours. Just showing why the experiment holds mathematically will hinder my progress. I don't know if it'd hinder your progress. Depends what you want to do. Depends what you're aiming for. You're doing soft matter physics. I don't know what soft matter physics is, but yeah, depends what you want to do. If you want to do more math, then probably you should lean into math more. How important is it to learn representation theory? I'm an undergrad right now, and I see it everywhere. Well, I mean, if you're a differential equations applied math guy, then it's probably not important to you whatsoever, absolutely at all. But you know, if you want to do representation theory, then representation theory is very important. And well, it depends. Yeah, if you like some algebra, you know, you might want representation theory. Yeah, it really depends on what you're into. Well, I'm glad you enjoy what I'm doing, what I'm putting out here on this channel. I think representation theory is awesome. Yeah. It's if you want to be a poet, probably not going to be very useful. But if you like algebra, then you should learn representation theory sooner than later. When talking about math research, you feel that 9 times out of 10 your arguments are lacking for pure math. Any suggestions? Yeah, well, I guess you just gotta hunker down, and I mean, there's only 2 things you can do to get better at proofs fundamentally, and that's reading proofs and writing proofs. You know, there's all these classic books that people suggest, like Polya's How to Prove It, stuff like that. Oh, you know what you could do? This may be too hardcore, because there's also, you know, computer proofs and human language proofs. Like in human language proofs, there's a delicate balance between, you want to be formal and rigorous, but you also want the human reader to like understand, to have an easy time understanding what you're saying. But if your problem is rigor at the moment, what you could do is try playing the natural number game or the set theory game, and on the lean game server. So this is there are a surprising number of mathematician poets. Yeah, well, I mean, it is a very creative endeavor, and we do love to romanticize our work. So, yeah, natural number game, logic game, even set theory game. So go here, and I mean, there's nothing more rigorous. You can't hide from the computer. So I would say go, you know, probably not the worst idea in the world to go here, but you get some practice. Valuable lesson you learned through your grad studies: it's okay as long as you find your own niche and be good at it. Yeah. Sometimes you just need a few tricks and insights to get started. Yeah, absolutely. One of your friends at Cambridge told you to do the same. He was like, learn lean and you'll get better. Well, there you go. Yeah, you can use Coq. Is Coq-based theorem proving going to be the future? Maybe. I mean, I don't know about that. It could be that or lean. I think lean is more, the people who are working in Coq are more minded to homotopy type theory, and univalent foundations, which are awesome. Maybe that'll be the future of mathematics as well. But I get the sense that Lean is more interested in making something available now that like the majority of mathematicians today can actually use as a tool, which we're still a ways away from, but it seems to me like they have more like the general mathematician in mind. Have I heard about Grothendieck Teichmuller group? It sounds too good to be true. That rings a bell. Grothendieck Teichmuller group. To the absolute Galois group of rational numbers. Programmed study Galois group. Teichmuller tower of groupoids. Fundamental groupoids of moduli stack of genus G curve with endpoints removed. There are several minor variations. Yeah. Rings a bell. I don't know much about it. But anyways, coffee's empty. So time to get first physically jacked at the gym and then mentally jacked in my office proving theorems. So I hope the same for all of you. Get some proofs done, and